So we're going to be talking about factors that affect equilibrium. Before that, we'll establish what is equilibrium. So if we take a look at this equation right here, it's a very generic equation. We have the coefficient, which is little a, little b, little c, and little d, and the molecule, big A, big B, big C, and big D. Chemical equilibrium is defined as when the rate of the forward reaction is equal to the rate of the reverse reaction. So basically that means the rate at which A and B disappear and form C and D is equal to the rate at which C and D go back and form A and B. According to Le Chatelier's principle, a reaction in equilibrium will respond to a disturbance in order to re-establish equilibrium. So here we do a picture to show this principle more easily. Say we have a room with two rooms, each with one person in it. If we add 3 people to the first room, we'll have 4 people in a room versus 1 person. This is a disturbance in the system according to Le Chatelier, and equilibrium will try to change this to reestablish a somewhat even room in both of the rooms. So 2 people here and 3 people here. But a reminder, in equilibrium, the concentration, which is represented by brackets, the concentration of the products does not have to equal the concentration of the reactants, which is why here there are 2 people here and 3 people here as opposed to 2 and 2. So for the first effect of change, which is represented in delta, effect of change in concentration. If you increase the concentration on either side of the reaction, the equilibrium will shift to the side with the lesser concentration. Again, we have drawn pictures, 2 rooms with 2 people and 1 person. If you add 1 person to the reactant side, you have 3 people on the reactants and 1 person in the products. According to Le Chatelier's principle and the effect of the change in concentration, this final product will change to 2 people on this side and 2 people on this side. Next is the effect of the change in volume. When you change the volume of a gaseous mixture, the equilibrium will shift to the direction that reduces the number of moles of gas. So for this, we have a reaction. N2 plus 3H2 is in equilibrium with 2NH3. This is the reaction that forms ammonia. So we have this large container with N2 and H2 gas. If we were to make the container smaller by reducing the volume, we have still N2H2, but because the container has gotten smaller, this is considered stress on the system, and according to Le Chatelier, we're going to try to change to equilibrium, and this reaction is going to push towards this product right here, which if you look back at the reaction, there's 4 moles of gas here and only 2 moles of gas here, which goes back and proves the point that the reduction in volume will shift the equilibrium to the direction that reduces the number of moles of gas. The effect of the change in pressure is very similar to the change in volume. Increasing the pressure of a gaseous mixture will cause the system to shift in the direction that reduces the number of moles. So we're going to have the same equation, N2 plus 3H2 is in equilibrium with 2NH3. So here I've drawn 3 cylinder type things with a weight, different sized weights. Here we have N2 and H2 again with a very smaller weight, which is representing not a lot of pressure applied onto the system. But here we've added a bigger weight, which has caused the pressure to increase as the weight pushes down on the gases. This is the stress in the system, and according to this right here, the equilibrium is going to shift to form NH3, which is represented here. And again, it has proven this by saying the 4 moles of gas here has changed the 2 moles of gas of NH3. Finally, the effect in the change of temperature. So in an exothermic reaction, an increase in the temperature shifts the equilibrium to the left. A decrease shifts it to the right. So here is a generic exothermic reaction. reactants are in equilibrium with products plus heat. Now, this occurs because if you were to add heat to the system, you would be adding heat to the product side here. By adding heat to the product side, you're creating a stress on the system, which, and according to Le Chatelier, will cause the system to try to push back toward the reactants so that it relieves the stress and helps the system go back into equilibrium. On the other hand, in an endothermic reaction, an increase in the temperature shifts the equilibrium to the right. A decrease shifts it to the left. So again, we have a generic endothermic equation here. Reactants plus heat is in equilibrium with products. So if we were to add heat to this side, we would be causing stress on the system on the reactant side, which will push the equilibrium to the products to try to reestablish equilibrium again. So basically, Le Chatelier's principle states that when a system is in equilibrium, any kind of stress that is put on the system will try to undo itself in a way that reestablishes equilibrium, whether it might be creating more products or more reactants.
Good job.